right, we're finally ready to jump into the math and derive some important functions for VAEs. I apologize if this video comes off as unfiltered, and that's because it is, and I haven't thought about this in a while. So we're gonna work this together and hopefully arrive at the result, and it'll be nice because I think walking through step by step kind of puts us into the shoes of the people who discover this and kind of the same thought process. So recall, right, what we're trying to do, we're doing this thing called variational inference. We're introducing a Q, right, that's going to try and approximate RP, right? So these things are looking at the probability of generating a code, Z, as code in the latent space for a given image that is put in, right? So to look at how these two compare to each other, we need a measure of distance between probability distributions. And if you've ever heard of this thing called the KL divergence, that does just that. So I'll quickly touch on it here, but I'll have a more in-depth video, so please go check that out. The way we write is we write it as the KL divergence between two distributions, P and Q. It's the measure of the distance between them, okay? And it's defined as the expectation over all P of the log of P, this log ratio, P over Q. Okay, so this is the KL divergence. If it's big, that means that the probability distributions are quite different. If it's small, that means they're similar to each other. Okay, so let's explore the KL divergence between these two distributions. So let's explore the KL divergence between Q, right, and P. And we're going to see how this will naturally lead us to a nice loss function. I'm going to bring you back to the beginning, and remember that the end goal we're trying to do is we're trying to maximize P of x, right? P of x is the probability that we see, it's the probability that given a data point x, that it's in our distribution, right? So you put in an x, which is, let's say we're dealing with images, you put in an image, and it's the probability that that image, if P of x is high, that means there's a high probability, right? That means in our constructed probability model of our x space, an image of, let's say, like if this x is an image, right, it's going to have a high probability. And if you have another image here, it's going to have another high probability. So we're building our probability space based on maximizing this P of x, okay? So let me get rid of all that, okay? Now, let's look at the KL divergence, and let's first expand this. So remember, using the formula for KL divergence, this is going to be the expectation over all Q of the log ratio. So log of Q of Z given X over P of Z given X, okay? We can use log rules, as I hope you are all familiar with. And we can say this is log of Q of Z given X minus log of P Z given X, okay? Then remember last video or the video before, we talked about Bayes' theorem and how that can be applied here, right? We can remember that P of Z given X is equivalent to P of X given Z multiplied by P of Z over P of X. And this is what made P of Z given X intractable in the first place, right? We can't exactly calculate it, but we can replace it with this, and you can see that replacing it with this actually introduces this term P of X here. So that makes us a little bit excited. So let's now, so this is like a side note, right? Now let's go over here and let's replace. So I'm going to draw an arrow here to make it clear that we're coming down to here. Okay, let's replace P of Z given X with this, and I'm going to actually do one more step. I'm going to now expand that log. So let me write it out. So this is going to equal to the expected value over all Q of Z given X of. First thing we have is log of Q of Z given X minus, now we're going to have log of P of Z given X is going to turn into that. So that's going to become minus log of P of X given Z minus log of P of Z plus log of P of X. And hopefully you can see that that just, again, follows from breaking this up using logarithm rules, okay? The next thing is, okay, I'm going to go underneath a line. And remember, this whole thing is equal to the KL divergence. So the KL divergence between q of z given x, p of z given x, correct, is equal to the expected value. I'm going to write these expected values in an interesting way, and you'll see why. So this is going to be equal to the expected value over all q of, I'm going to first write negative log p of x given z. Okay, that's my first expected value. Then I'm basically splitting up the expected values. Then in the next one, I put this one already. In the next one, I'm going to put this guy and this guy. So it's going to be log of q z given x minus log of p of z. And then plus, technically I have to do the expected value over all q, but remember q is z given x. So there's no dependence. P of x doesn't depend on q of x doesn't, there's no relation between the two. There's no variable that's similar between the two. So I can pull this log of p of x outside of the expectation, because taking the expectation over z's won't affect this value at all. So this is plus log p of x. Okay. Then what we can do is this log of p of x is making me excited, because let's isolate for it. All right, so let's solve for log of p of x. Okay, so how I'm going to do that is I'm going to bring this guy and this guy to the other side. So I bring this guy to the other side, the negative pretty much goes away. So I get positive expected value. So let's first write this term, right? This is I first have the KL divergence between Q and P. Okay, then I add the expected value over all Q of log of P of x given Z. Okay, then I'm gonna bring this over. So basically it's gonna become a negative here. So I'm just gonna flip what's inside. I can basically just bring it over to the other side and negate it, correct? Which means the P, it's gonna become minus, right? It's just gonna become minus expected value of all Q of x over all Q of, again, just literally bring it over to the other side and change the sign. So this plus turns into a minus. So we get that minus is here, and we get log of q z given x minus log of p of c. Okay, let's break this down. The first thing we know is that a property of KL divergence is that it's always bigger than 0. So this term here, okay, this is our original KL divergence term. This will be bigger than 0. Okay, so immediately what we can do is we can rewrite and say the log of p of x. We can ignore that term now and just say, because it's positive, this log of p of x is going to be bigger than or equal to, right? Because this thing is either 0 or bigger. So this thing is going to be bigger than or equal to, okay? This term I'm going to leave the same, expected value overall q of z given x of log p of x given z. Okay, that's fine. Minus this term, if you notice something, right? This little thing right here, inside here, can be rewritten as log of, because it's a difference, we can rewrite it as a quotient, right? And if you notice, this is, in fact, this whole term is actually a new KL divergence, the KL divergence between Q of z given x, right? And now instead of being with P of z given x, now it's just P of z. Okay? And we have just derived what is called the ELBO function. ELBO. Evidence-based lower bound. Okay? Because I guess it's based on evidence, the evidence that we're observing here, and then it's a lower bound. Why? Because we're saying that this is a lower bound. So I think that's enough for this video. In the next video, we're going to dive deep into what this actually means, but we derived it now. Congratulations. Okay, make sure you watch the next video though, so this all makes sense. Otherwise, this is just a bunch of random math and numbers and letters. Okay, see you next time.